All right, so let's continue with an example of a first order integrated rate law problem. But first, look back on here. There's two adjustments to make. I did miss a negative in here. Right here in the integrated rate law right here, there should be a little minus sign right there. And then also right here, there should be a little minus sign. Now, I did do that. It turns out that I did it correctly right here and right here. And these are the important ones. So if you want to highlight something in your notes, highlight these guys right down here, because the ones that are in the form of y equals mx plus b, those are correct. And that's okay. I just forgot this little negative right here and that little negative right there. And then when you translate them, I got that part right. But now that we have those equations right, now I have this handy right here. And on the back side of this sheet, you should have some example problems right here using the integrated rate laws, and I'm going to work right from those, and then I'll reference this sheet right here as we go along. And then you can have your calculator out as you go, and you can try your calculator and make sure I don't make too many calculator mistakes as we go along as well. So first of all, this is number 1, and it says a certain reaction has the following general form: A goes to B, and at a particular temperature we have an original concentration of 0.1 molar. Concentration versus time data were collected. A plot of the natural log of concentration versus time resulted in a straight line with a slope value of 0.25 when graphed the slope of the line is negative. So that's enough hints for you that you should be able to look on here and you'll say, okay, there was a graph with a straight line and it had natural log of concentration. Which one had natural log of concentration? Oh, this one right here, versus time, straight line with a negative slope. So that means it's a first order process right here. So we're going to be using these equations in that particular question. And that's the one we're going to focus on. So it's first order, and that's your first job, is to understand which set of equations to use once you encounter an integrated rate law problem. All right, so then let's go on to letter A right here, and it says write the rate law, the integrated rate law equation, and the numerical value of the rate constant for this reaction. So first order is always rate is equal to K, and then times the reactant, which is A, and then it'd be to the first power. All right. The integrated rate law, you can just copy it right off of here. Use this one right here, the y equals mx plus b1. So that would be the natural log of concentration at some time is equal to negative kt plus the natural log of concentration original. So that I just took right off of here. That's this equation for a first order integrated rate law. And then it says find the slope. So the slope, remember, is k. So if we know k, then we know the slope, and it tells us that the slope value, well, it tells us the slope value right here, which is k, which is equal to the slope, which is equal to negative 0.25. And it doesn't tell us what time units they use for this, but let's say that it's seconds, so then it would be 1 over seconds or 1 over time. And it tells us that when graphed it would be negative, so that's why I put the negative sign right there. So that's letter A. Letter B, it says calculate the half-life for this reaction. So now we need to look on this sheet right here and find the half-life equation. Half-life equation, first order, T1 half is equal to natural log of 2 divided by K. Okay, T1 half is equal to the natural log of 2 divided by K. All right, the natural log of 2, I can do that on my calculator, so try that on yours right now. Make sure that you know where the LN button is, right here, LN, and then type in 2. And the natural log of 2, hit enter, that's 0.693. And sometimes you'll see this equation not written as the natural log of 2, you'll see it written as 0.693 divided by k. It's the same equation, it's just that, that's where it comes from, is the natural log of 2. All right, then for this we'll take 0.693 and we'll divide it by that rate constant, which is 0.25, 1 over seconds. And for this, we don't put in the negative because you can never have a negative time. So 0.693 divided by 0.25, enter, 1 over seconds, so we end up with 2.77 seconds as our half-life. All right, letter C then, calculate the time required for the concentration of A to decrease to 0.025 molar. So now we're going to use the integrated rate law equation. And they're asking us to find time, because that's the only equation notice how this one doesn't have time in it. This one has half-life time, but it doesn't have a t in it. This one's got time in it. So when they're asking for time, we're always going to use these integrated rate law equations right here. So let's write this equation down again, and then we'll solve from there. So this is natural log of a at some particular time is equal to negative kt plus the natural log of a original. And some people like to rearrange the equation. I personally like to do that, but I know that a lot of high school people like to just put the numbers in and then solve for what you're going to do. So I'll do it that way to start with. So first of all, the concentration rate here has decreased to 0.025. So we'll type in natural log, or we'll put in natural log of 0.025. We can drop the units now because the natural log, remember, is going to be an exponent, and that doesn't have units. And then negative, and then the k, remember they told us the k right here is 0.25. Okay? And then we put 1 over seconds as those units, and the minus sign's right there. So we've got the minus sign right here, negative 0.25, 1 over seconds. Remember that the slope is k. If you forgot that, look up here. Remember the slope is k, and here's k. And then we have t, that's the thing we're looking for, time. And then plus the natural log of the original amount. So the original amount, it tells us, was 0.1 molar right here, A original. So 0.1 goes right here. All right, now a bunch to put into our calculator. So I'm going to zoom out just a little bit so you can see the calculator at the same time. Let's do the natural log of, let me get it so you can see it again, 0.025. And so I've got negative 3.688, and then over here I'll still have my negative 0.25. I'm going to drop the units for right now because I know I'm not going to have any units from these, and this is going to be 1 over seconds, and then when I divide it I'm going to end up with seconds. This is time, and then the natural log of 0.1. So natural log 0.1 ends up being negative 2.3. All right, so let's manipulate this a little bit. Let's add 2.3 to both sides. Excuse me. And let's find that out. This is going to go away then. So negative 3.688 plus 2.3, enter, and we end up with negative 1.388. is equal to negative 0.25t. Divide both sides by negative 0.25. Divide this side by negative 0.25. That's nice. The negative is going to go away because time, of course, always has to be positive. So then we're going to take this number and we're going to divide it by 0.25. Enter. Oh, I forgot to put in negative 0.25, but this should be a positive number then. And so our time should equal 5.55, and then the units would be seconds on that. All right, that's an example of a first order integrated rate law problem. We had to figure out what order it was, and then we put down all the equations, and we used this as a map or as a guide. So keep this aside, and we'll do a second and a 0th order ones coming up in a bit.